Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Good morning, everyone. My name is Mohammed Saad. I'm a current student in information technology, master's student in information technology and computer science here in Ahliya University. And I'm supposed to be here to present my thesis, but I spent the last week thinking of how to present it in a very smooth and easy way rather than a complicated with a slice full of equations. So I decided to give a brief introduction on quantum computing because I noticed recently that whenever the word quantum is brought to a discussion, people get scared off and everyone thinks it's a very complicated field of study, only meant for people like Stephen Hawking, may he rest in peace, and Einstein's, for example. So I prepared this presentation to give this brief introduction on quantum computing. I was hoping there would be baccalaureate students to encourage them to look into this research field. And the first question everyone would ask would be what a quantum computer is. Everyone asks, okay, where is the processor? Where is the registers? Where is RAM, storage? In order to understand quantum computers, we need to let go of everything we know about classical computers and look into this very simple model. What we have in the middle is a diagram of a quantum computer, and those circles inside are nothing but particles. In other words, electrons, the building blocks of this universe. And scientists found a way to use them and harness nature processing power to be able to help us solve our problems. So, to put it in a very simple way, a quantum computer is just a shell that houses a number of particles. In this example, for example, n particles. And we give it n inputs, and it gives us out n outputs. So we give it an input in the form of a vector and an output, and it gives us back an output in the form of a vector. So when we look at electrons, we find that they have this intrinsic property called spin. An electron is always spinning in one direction. And we present this, we call this spin either a spin up or a spin down. And I guess one of the scientists in early 60s realized that if it can spin up or down, why don't we use it as a bit? It can represent a 0 or a 1 bit. This here represents how an electron spins. Either it spins down or up, as you can see. And as you can see, that's a vector representing the 0 value and a vector representing a 1 value. There is a special property of electrons working in the quantum realm. And here is where the magic appears. There is something about the electron. It can be also 0 and 1 at the same time. It's something that we don't understand. Intuitively, we cannot understand what that means. But when we think of it as probability equation, we can think of an electron can be 0 and 1 until we observe it. Once we do measurement and look at it, that's when it has to collapse into either 0 or 1. But before we do that, it's both. So we keep our quantum computer without any observations, and it represents all our vector space. We will see that in a minute. So the property that we talked about is called superposition, because we can have 0 and 1 at the same time. This is just a different representation of it. As you can see, it's a ground state, 0, 1. And our superposition is represented by this equation, the 0 vector and the 1 vector, and each with an amplitude. The amplitude here represents the probability. So the probability of the electron being 0 when we measure it, or being 1 when we measure it. So we represent our qubit using something called a block sphere. It's a unity surface, a unity spherical surface, and our vectors are unity vectors that can take any direction inside this space. It means our electron cannot just be 0 and 1. It can be 0 and 1 and a combination of many bits at the same time, depending on where it's facing. If it's facing up, then it's 0. If it's facing down, then it's 1. If it's perpendicular to the 0 or 1, it means if it's facing east, your right, or your left, then it has a 50-50 probability of being 0 or 1. As we will see, in a qubit, when we think of qubit states as a vector, you'll find that we can have one qubit, and it can represent either 0 or 1 or both. If we have 4, we can represent any number that needs only 4 bits to be represented. And then we can perform operations on it, as you can see. For example, the 4 vector and the 5 vector, if we sum these together, we will come up with electrons with different orientations. So what we do by the end of our experiment is measure the state of every electron, and that will give us the solution. This is how we represent our vector space, or the state vector. And as you can see from mathematical statistics, that the probability, the summation of all probabilities should be 1 by the end of a summation process. So in classical computers, we're all familiar with the word gate, an AND gate, an OR gate, and a NOT gate. And their quantum counterparts are simply these. So what are these? If anyone have been familiar with matrices, these are simply transformation matrices that rotate our particle. So if our particle is facing up, and we use that X operator, we rotate it 180 degrees on the X axis. So they are similar to the AND and OR gates. As you see, one of the algorithms that I want to talk about is called the Grover's algorithm. You can relate to this because it was invented to do a very basic search, database search. And I'm sure all of you are familiar with retrieving information from a database process. We all know that to search an unordered set of a database, we required n numbers of operations if we have n entries inside the database, correct? So, for example, in classical computers, it takes an order of n operations to search for an entry, a specific entry m inside the database. A quantum computer with n qubits, where n equals to n, can store n entries. And it can retrieve this entry in less operations. And that will, as you will see later on, it can retrieve an entry from the database in a square root of n operations, which is very efficient compared to the classical computers. So if we want to search, for example, for entries in a database that has n entries, first we will have to reset all the particles inside our computer, and we do that by normalizing. As you can see here, I present all the states of all the positions inside the database, or all the indexes, and we normalize all of them. And then we apply one of these operators we showed you, called the phase flipping operator. So it flips the only address that corresponds to our query. It flips the phase. It means the probability becomes a minus, a value with a value minus probability. And after that, all we do is use another operation called the inverse about the mean. So basically, it inverses our m about the mean, and by repeating this procedure, we repeat it r times, which is the square root of n, and by doing so, the mean will always descend until it reaches the 0 line. When it does, then we have our solution. And we found out that we only have to do square n, as you can see, square n operations in quantum computers. But in classical computers, we have to do n operations. And if you think about it, if we have a database that has only 4 entries, okay, a classical computer will have to do 4 operations to find any entry inside it, correct? But a quantum computer, in this case, would only need a square root of n, which is square root of 4. So it would do only 2 operations to find our entry. Now think of it in bigger terms. If it was, for example, 100 entries, a classical computer would need 100 operations to find your entry. A quantum computer would only need 10. If it was 10,000, a quantum computer would only need 100. When its classical counterpart would need 10,000 operations to find a single entry. So this is a major upgrade when it comes to database search. And lastly, I would like, most of people they think that quantum computers are not accessible, it's hard to find. How are you going to program or design algorithms for quantum computers? Well, I would like to introduce IBM Key Experience. Basically, IBM researchers, they build their quantum computers and put them on cloud for us. So any of you can to IBM Q, just search for IBM Q Experience, sign up, create an account, and you can use their quantum computers. This is how a quantum computer program looks like. It's even more visual and easier. Thank you. I hope you enjoyed it. I hope you learned something, and I hope both the faculty and student could encourage each other to do more researches in this field. This is a very new thing, and I would expect that 10 to 15 years from now, you will have quantum computers peripherals in every computer, even here in the Ahliya University. Thank you.